Everything we do is available on biomedicals.com. Go check the website out. Let me know if there is any feedback. Don't forget to like, subscribe, unsubscribe, whatever you have to do. And check Patreon as well if you want to support this project. Whew. That's normally what a robot should say, but...
Welcome to a new deep dive. Today, we're peeling back the layers on something really fascinating, EEG technologies. We were inspired by this interactive guide to EEG technologies. And, well, our mission is to explore how we actually listen in on the brain and maybe understand what these incredible tools can tell us, about ourselves. We'll try to unpack everything from the basics right up to the cutting edge stuff. Looking at the trade-offs, some surprising insights for you along the way.
Absolutely. And, when we talk about listening to the brain's electrical whispers, it really all begins with the electrodes. Their design, the material they're made from. It's fundamental. It massively influences the quality of the data we actually capture.
Right. Getting the clearest signal possible.
Exactly. Right from the source.
And to make sure we can actually compare that data reliably between different studies or different people.
That's where the standardized international placement systems come in. They're crucial. They're quite smart, really.
Yeah.
They adapt to individual head measurements. So it ensures consistency, reproducibility, which is vital for research.
But that brings us to a really critical point, doesn't it? Is every method of listening equal? Or are there always big compromises?
That's the core question, really. We often talk about the spectrum of invasiveness. And it highlights this direct trade-off you mentioned.
Okay.
The closer an electrode gets to the actual brain tissue, the higher the signal quality you're likely to get. Much cleaner data. But, as you'd expect, that comes at a cost. A clear cost.
Increased surgical risk.
Precisely, increased risk. And what's really interesting is you see these distinct sort of step-like improvements in the information quality as you increase invasiveness. It's almost like leveling up the detail you can see.
Wow. So if you have these big differences in invasiveness and what you get out of it, how does that actually play out? In the real world, how do doctors weigh those risks?
Well, take a really critical situation like planning epilepsy surgery.
Yeah.
The choice between highly invasive techniques becomes absolutely paramount. So you might be choosing between, say, stereoelectroencephalography, SEEG. That's where tiny electrodes are surgically placed deep inside the brain itself, really trying to pinpoint where seizures start.
Right inside. Okay.
Versus something like Subdural Grids, SDE. Electrode arrays positioned right on the brain surface. And recent evidence from a large international registry actually directly compares these. It shows some significant differences in their safety profiles and how effective they are diagnostically. It's all about getting the most precise information possible while crucially minimizing risk for the patient.
So beyond the actual hardware, the electrodes and wires, what are these technologies letting us see? What kind of information are we actually picking up?
Yeah, good question. They essentially allow us to visualize dynamic brain rhythms, different frequencies that we know are associated with different mental states.
Like brain waves.
Exactly. Brain waves. You can think of them like the brain's different musical notes almost. You have delta waves, those slow, deep rhythms of sleep. Then theta for that sort of drowsy, meditative state. Alpha is that calm, idling hum when you're maybe unfocused but awake. And beta waves, those are the faster frequencies you see with active thinking, concentration. These rhythms, they're really the fundamental building blocks for analyzing EEG data.
Okay, so it sounds like ultimately the choice of which EEG tech to use, it's always driven by the specific goal. You pick the right tool for the job at hand.
Precisely. Yeah, exactly right. Whether it's for precise clinical diagnostics, like we discussed with epilepsy, or cutting-edge neurological research trying to understand brain function, or even, consumer products now. Things like advanced sleep trackers or maybe meditation feedback devices. Different methods, different modalities are tailored for those specific contexts. It's always balancing the detail you need with safety and, practicality. We're even seeing really interesting progress in neurofeedback, helping people learn to regulate their own brain activity.
Right.
And of course, the very experimental work in brain-computer interfaces.
Allowing thought control.
Yeah, potentially. It's early days, but fascinating.
This has been incredibly insightful, really. Thinking about everything from those tiny electrodes just sitting on the scalp, all the way to these complex rhythms mapping our thoughts and these huge decisions made in surgery. It really does show how much we can learn just by, listening in. It absolutely underscores that point. Understanding EEG, choosing the right approach. It's always about balancing signal fidelity, what you want to see, with the practicalities and the risks involved. It's a constant balancing act.
Which I suppose raises a big question for you listening right now. As these EEG technologies keep getting better, more sophisticated, maybe even more integrated into our daily lives, think wearable tech perhaps, or smart environments reacting to our brain states, how might our fundamental understanding of consciousness, of brain function itself, actually shift? What new frontiers could these insights unlock for all of us? Something to think about.
Okay, so there's a human in the loop, just in case you're wondering.